Welcome back. In this lesson, we're going to switch up a little bit. We spent the better part of this series, the last 18 or so videos, talking about probability and probability distributions and those kind of things and their properties and their behaviors for both discrete and continuous systems. All right, but all along we've been kind of keeping our eye on how can we use probability and sample data to predict a population's behavior. All right, and so in chapter 6 of the DeVore text, which is the one we're going to start on today, we get into something called point estimation. Okay, and that's the beginning of our ultimate goal in this series, to understand the statistical basis for what we're doing on this. Okay, now it's kind of a different animal. It's a little bit different than what we did with probabilities in our calculations, but it has its roots and everything. In fact, we'll be using the expected value and the variance a lot, as we start to move forward from this. Okay, so we'll kind of set up today with some of the notation that's used, and then we'll show you some experiments that we can do, and then we'll kind of show you how the whole basic setup works for this. All right, so without further ado, here we go. All right, so point estimation basically is used for estimating statistical values. All right, and the notation that you're going to see is used repeatedly. It's in the chapter in the book, and this is kind of how I've always learned how to do it anyway, is to make a notation such as the following, okay, that we're going to define a theta character as a parameter or a statistic to be estimated. Now, generally, this is some population value. Most often, it's like the population mean or the population standard deviation. It could be anything. It could be, anything that could be a statistic can have, can be used to model, okay. We're going to indicate a theta with a hat on it, this little triangular pointy thing over the top, okay, as being the point estimator for that value that we're after. Okay, it's a statistic or formula for calculating a single number from the data that is an estimate of theta. Okay, now remember that in a video a couple lessons back, we talked about the statistics and how they have their own probability distributions, and we spent a lot of time kind of building up an example in that video. And so, like I say, if you need to flip back, that might be a good one to kind of understand if you're still a little fuzzy on all of this. All right, but what we got to remember is that statistics are probability. Have probability distributions. They are random variables with a PDF. Okay, and if we can keep that in mind, then we can do all the stuff that we've learned up to this point to work with that estimator. Okay, so to give you kind of an idea, what is an estimator? Okay, assume that we're interested in estimating the population mean for a particular problem. Maybe it's a survey, maybe it's number of cases of illness or whatever the case may be. Okay, we could do any number of estimates for that particular value. All right, so if this is what we're after, this is our theta is equal to mu. Okay, possible estimators could be any of the following, and all of them work in certain circumstances. For the mean, for the population mean, I could take a sample, and again, remember, a sample is a representative subset of that. Generally, it's not the entire population for this to work. Because after all, if you had the entire population of data, you wouldn't need to do an estimator. You could just calculate whatever value you were after. Okay, but our theta hat in this, we could use X bar, a sample. So maybe I have 100 million samples and I go take 1,000 survey results. Okay, I could use that mean. Well, how could I correlate this mean back to the population? Okay, so it kind of makes sense. A sample mean could be a good predictor of a population mean, depending on how you chose your sample. Again, this is all random, and so we have to follow all our rules of probability when we do that, but that seems pretty logical. You could also take your estimator as being the median, the sample median. I take a sample and I take the middlemost value and I say, I'm going to use that as my estimate for the mean. Okay, and that may or may not be as good. Again, it depends on your luck of the draw, so to say. Okay, but this one tends to work very well for symmetrical distributions, and if we start taking large enough samples, then it really starts to work out pretty good. That middle value will be somewhere near the mean, but not guaranteed. Again, all of these are estimates, so getting it 100% dead on is not a guaranteed fact. Okay, another one that works is we could be taking the lowest value and the largest value of our data and dividing by 2, adding them together and dividing by 2, taking the average of the top and the bottom of my sample. Okay, so again, that's another estimate of how do I get to the mean. Okay, and so this works if you have kind of a uniform distribution, or that equal likely outcomes or something. That one tends to do a little bit better than some of the others. Okay, but all of these are possible point estimators. Okay, but the question becomes, which is best? Okay, so we've got to come up with a mechanism for how do we evaluate which of these is the best estimator. They may all work, but some are better in certain circumstances than the other. And so the point of point estimation then is for us to come up with a tool set for how do we evaluate the effectiveness of whatever we choose to estimate. I could just as easily have said the number of occurrences of the number of 3 in my data as an estimator for whatever my population is. It may not be good, but it is an estimator. Okay, so we've got to come up with a way to kind of qualify what we're doing, and is it a good estimator or not? Okay, all right. So to do this, we have to understand a couple of things. All right, first off, we have to understand some terminology. Okay, and the first term that we're going to talk about is called bias. Okay, and basically this is a systematic error that's built into measurements. Now this isn't error like you record something wrong or you punch the number wrong in your calculator or something like that. So it's just basically it's the error that's built into the measurement. Okay, so the way we remember this is that we looked at our theta and our theta hat and say, hey, they're random variables and both have distributions. Okay, that's kind of the premise here. And so ideally, if I draw, for this argument, I've set it up as normal distributions, but it could be anything. And you can see that, I've plotted the distribution of this theta, whatever it is kind of some sort of normal bell-shaped kind of curve. Okay, and then ideally, if we have a very good estimator of theta hat, it would follow this curve exactly, okay, at all points for all values of x. Okay, and but in reality, more likely, it's going to have its own distribution that is either, maybe it's not as high, maybe it's offset, in which, in the way I've drawn it, I assume that they have the same peak value, but it's just the occurrences and the frequency are a little bit different on this, okay? And so at this point, we define the expected value of theta hat, and at this point, we define the expected value of theta, which is just our theta parameter, okay? And then bias is the difference that exists between those two values. All right, so if we want to have a good estimate, then I want this line to line up over the top of this line. Okay, now that, again, as we were talking about visualizing data, expected value is not all that we have to look at. We also have to look at the variance, which is how does this thing, how is this data spread out, relative to that point. Okay, because again, we're trying to come up with an exact replica of the theta distribution in our sample. And again, it may or may not be possible. Okay, so the definition of an unbiased estimator, which is what we want, is when the expected value of theta hat is the same as the actual parameter that I'm looking for. Okay, we can also talk about the degree of bias as being the difference between those two parameters. Okay, and then if it's unbiased, then theta hat is approximately the same as theta. That's the whole moral of point estimation. Okay, so what can we do to come up with a predictor that in which the bias isn't, a significant factor? All right, so if we talk about a couple of examples here, just kind of illustrate what we're doing. First one we have is a binomial experiment for a random variable x. Okay, now, what we're saying is that the probability of a success is some script value p. That's the same notation we've used back when we were doing binomial. Okay, we're going to use an estimator theta hat then as being my data point divided by n. Okay, which would be the number of occurrences in my sample. Okay, we're going to use that as an estimate of theta of my parameter being equal to the probability p. Okay, so if I do that, we can calculate the expected value of this as then being the expected value of x divided by n. Okay, and from the binomial definition that we talked about a couple of videos back on this, then we know that the expected value of a binomial is n times the probability of success. We get that, and so if n times probability of success over n is equal to p, well, that's the same as what my population was doing. Okay, this one, right? Okay, so this means then that theta hat equal to x over n is an unbiased estimator of my population statistic. In this case, the probability that we're after for a particular data point. All right? Okay, so that's the first one. Like I say, fairly basic, just kind of trying to get our feet wet. Let's try one that's a little bit more challenging, all right? Okay, we're going to assume that we have a set of data, a set of x's, in which my xi are independent, and uniformly distributed on the interval 0 less than or equal to xi less than or equal to theta I. Okay, so what we're after is my population statistic is the maximum value on this. Okay, and that my random variable can be anywhere between my max value and 0 on this. Okay, and so what we want to know is y, and this is just another fancy way of saying theta hat being equal to the maximum of all the data points in my sample, an unbiased estimator of theta. Okay, now again, we're assuming n is a constant. That's equal to the number of observations that we're making. Okay, now for this, we can define for this variable y being the maximum, the max function has a distribution that's given as the marginal of our y as being n over theta to the n multiplied by y to the n minus 1 for some y value on that same interval, 0 less than or equal to theta. And again, the statistic we're after in this is the maximum value. All right. So what happens is, just like before, we come in and we calculate the expected value of my function. As we'd expect, expected value of y, so that's the expected value of my theta hat. And if I plug in this formula in, this maximum value of the population is a constant. That's an unchanging value. Okay, so theta to the n, okay, and then we're going to multiply that by then, for expected value, y times the probability of the y. And again, I pulled this piece out. This should be over next to this. I pulled that out, and I'm going to integrate over all values. So my upper limit is theta, my lower limit is 0. And when I do that, this y times y to the n minus 1 dy, okay, what will happen is when I integrate it, I'll be left with the formula of n over n plus 1 times theta. Okay, and so what we see on this is that, the expected value of my estimator here is equal to n over n plus 1 times theta. This is a biased estimator, right? Because depending on the value I choose for n, okay, it will underestimate the value of my theta. So let's just say we put a 10 in here, right? And I put, a 2 for n, and that's 2/3. My expected value of my estimator is 2/3 of the true value. Well, that's not really good. But if I put 1,000,000 in here for n, now it's 1,000,000 over 1,000,001. That's basically the same value. I would expect to be able to find it, okay? But historically, for all values of n, my estimator will underestimate theta. Okay, now that doesn't mean that we can't use it, but it means that we need to make a revision to our estimator. Okay, so let's try, maybe we can modify this. Can we improve our situation so that it does become unbiased? And one of the tip-offs that tells me that that's possible has to do with the fact that the only term outside of my theta, this n over n plus 1, if you will, the n over n plus 1, is that it's only a function of n, right? And n is constant. We declared that when we started doing our experiment. Okay, so if that's the case, now maybe there are some things that I can do. So let's try this one. Let's define a new estimator. Again, this is my theta, my new theta hat, as some variable z. Okay, and that's going to be equal to then n plus 1 over n times the maximum function, the maximum value of x1, x2, and xn. All right, so what happens is this is what we had before. Okay, this guy was my y. So we're going to say that we're going to make this as n plus 1 over n multiplied by my y variable. Okay, and we found that the expected value of y here, okay, was this n over n plus 1 over theta. That was the thing that we did up here just a few seconds ago, right? Okay, I'll get that cleaned up a little bit. Okay. All right, so if I take this constant, the expected value of y, and I multiply it by a new constant, n plus 1 over n, look at what happens. N plus 1 cancels this, and n cancels this. That function now equals theta. Okay, which means that the expected value of z, my random variable z, which was my new estimator, is equal to theta. This is now unbiased. So all I have to do is basically choose the maximum of my sample and multiply it by n plus 1 over n, and I will get an unbiased estimator of the statistic that I'm after, in this case, the maximum value. Okay, so if you remember back in like one of the early videos, early on, when we were talking about standard deviation and sample standard deviations, and we started seeing, formulas, but then these n's and n minus 1s were all running around. This is where they're coming from, okay, is they're coming in from this unbiased estimator to be able to come up with that. Okay, so anytime you see like an n or an n minus 1 or an n plus 1 or something running around in a formula that just seems kind of out of nowhere, chances are it got its roots in this process, this biased calculation of trying to come up with an unbiased estimator. Okay? All right. Now, we still have a couple of issues that we need to talk about. The first one is that, in this last example, we could also come in and say, well, let's try a different random variable. So again, this is my theta hat. Let's try a random variable w, such that I make it 2 times the sample mean. Okay, and you know, for a uniform distribution, if the sample mean is the middlemost value, if I double that, I'll get the upper value. Okay, it turns out this guy is also an unbiased estimator for the same calculation. So what do you do when you have two or more unbiased estimators? How do you determine which is better? Okay, and that's the other challenge that we have. So the first thing is we got to find an unbiased estimator, but again, recognizing that there could be multiples of these, how do we make a selection to choose which is better? Okay, and that's the trick. Okay, so the answer to that question is that we're going to choose an estimator with the smaller variance. All right, and so if you remember, we can say that the variance of, say, some random variable x was the expected value of x squared minus the expected value of x, quantities squared. Okay, that we can take advantage of this. And so now I'm not going to do it in this lesson. I'm going to assume that we're comfortable doing this. But if you did that calculation for our random variable z that we defined earlier, you would get 1 over n times n plus 2 times theta squared would be the variance of that random variable z. And then if you repeat the process for our new random variable w on this, again, z was where we were just taking the n plus 1 over n times that max function, and w is that 2 times the sample mean. If I do the variance of w, I get 1 over 3n times theta squared. Okay, and so what do you notice about these two formulas? Okay, we're after the one that's the better estimator is the one with the smaller variance. There's less error associated with the width of that plot that we showed you earlier on. That for these two equations, for all n greater than or equal to 1 on this, Vz is going to be less than Vw. All right? Okay, and so z then ends up being a better estimator of our function here. Okay? Okay, because Vw will always be a larger value of that for any value less than 1. And I can prove that by saying that's 1 over 1 times 3 when n equals 1 for this guy, and this guy is 1 over 3. Again, everything multiplied by theta squared, and then if I put in n equals 10, I get 1 over 10 times 12 versus 1 over 30. This guy is 1 over 120. You see he's clearly smaller. And the larger the n, the better z becomes. Okay, at n equals 1 exactly, meaning you're only taking one data point, they basically behave the same way. Okay, but for this, z is a better estimator. Okay, now, so the idea, the premise that we have in this is that what we're after is that estimators with minimum variance is what we're trying to find. All right, so this is kind of the heart of what we're trying to do, and that's kind of why I have a star next to this, is that among all unbiased estimators of my population statistic, or what we're calling as theta, we want to choose the one with the minimum variance. Okay, and the book and in practice, I refer to this as the MVUE, or the MView. Okay, and so for us, it turns out that our z, as we defined it in the last example, was the MView for the previous example. Okay, but the population mean being equal to the sample mean is the MView for mu when the sample distribution is a normal distribution. Okay, in fact, that should be population median, sorry, is the same as the average value when the sample distribution. Okay, all right, so but now there is still one other little issue that remains. Okay, again, we talked about trying to come up with curves that exactly followed my theta. Okay, and now the biggest problem, first off, is that there is no formula or methodology that tells you what the minimum MVUE is. You basically have to fit the data and kind of work with this. And so there's some skill and kind of some mathematical prowess that's required to come up with these estimates. Okay, there's no generalized procedure that oh, you add 3 and integrate and whatever, when boom, it'll pop out. It doesn't work that way. Okay, but what we're looking for is the other problem that we have is that some MVUs can be better for certain regions than others. So let's suppose that I go back to my normal distribution for my parameter for my point estimator, or in this case, my population parameter, the statistic distribution that I'm after, my theta, if you will. And so let's say that I have a z distribution sample. And again, I use z and w. These aren't necessarily the ones that we use up there. I just use the same labels on this. And this guy could have some distribution that looks something really crazy, but then from about here on, it could be perfect. Okay, and so from this location, he's a great choice. So if I'm plugging this away against whatever values my random variables are, on there, it would be a very good estimator from this point on the distribution. Okay, and likewise, I could have a W that's horrible over on this side, but it tracks very, very closely here. So from about here on, it's a good estimator. Okay, and so you can have estimators that you qualify, and we kind of did that back up here. When I made this statement, that's what we were doing. And saying that this guy tracks very, very close when n is greater than or equal to 1. Okay, but it turns out that, obviously I can't have an n anything less than 1, but in some cases, depending on the math, it's possible that this is the qualifying statement, that when n is greater than 1, z is a better choice. But, if I could have a decimal value on this, well, then this guy would blow up a whole lot faster than that would. Okay, and so we've got to kind of be careful, but that's kind of the moral of the story. Again, there's a whole lot more to what we're getting into with point estimators. I'm just kind of giving you kind of an introduction to the basics of this as we start to kind of look. All right, okay, so hopefully that kind of makes sense to us there. Okay, but again, it has to do with certain reasons. You can always qualify a function so that it fits a little bit better. Okay, so what we can do then is we can define what we call, as part of this MVU calculation, the standard error of an estimate. Okay, so if this is my variance of my estimator, then the standard error of my estimator then is just the standard deviation of that estimator. It's the square root of the variance. So that should be no surprise. Okay, now what we find out is that the standard error itself will often involve parameters that must be estimated. Okay, that, in this case, maybe it's not possible for me to get the true population value, so I'm going to do an estimate of my estimators, in order to be able to do my calculations, and so we need to take that into account on our error. So what happens when that happens is sometimes I can do it with an estimator, or sometimes I do it with a sample of my estimators. Okay, it's kind of a weird rabbit hole almost that we're starting to go down on this. But just kind of conceptually, I just want you to kind of think about it. So let me show you kind of in an example what it is that we're talking about on this. Okay, suppose that we have a random variable x, okay, that represents the number of scratches on an item that's being produced in fabrication. And for n equals 150 samples, we get the following breakdown on the number of scratches. I had 18 when, no scratches 18 times, 1 scratch 37 times, and so forth and so on, all the way up to 7, in which I actually had 1. So this, we don't know why, but this is part of the quality assurance program that this data exists. Okay, if we assume that this is a Poisson distribution, fits the data best, okay, and again, this would be something given. You would plot the data and try to come up with a curve, so it could be a gamma curve or a normal or whatever. In this case, we're just going to be given that it's a Poisson. Then we know that my random variable x is Poisson distributed on x with some parameter lambda is equal to e to the minus lambda x over x factorial. Again, we've covered this in a previous video, so if you need to review, by all means, please go back and look at our Poisson distribution video, and we'll explain this formula in more detail. Okay, and then my x values go all the way from 0, 1, 2, all the way up to 7 on this. Okay, for the Poisson distribution, the expected value of x and the variance of x both all correlate back to this lambda parameter for the Poisson distribution. All right, so what we want to do is, so that's my population data, or what my sample, and what we're using to represent the population. So if I can get this guy, I can define everything. So what we're going to do is we'll come up with, well, how do we estimate this parameter? Okay, and that's always the challenge in this. So let's take our point estimate, and let's just choose that it's the sample mean. Okay, basically I take up all of the numbers that I've got, and I divide by the number of readings, and we're going to use that as an estimator. Now, it may be good, it may be bad. We don't know until we do the check. Okay, so we're going to take 1 over n over the sum of the xi. And again, what this 1 over n tells me is that I'm assuming that in my data that a 0 is equally likely to occur as a 1, as a 2, as a 3, so forth and so on. And then that's how we get the distribution of it. Okay, all right, so let's go through and we're going to calculate the expected value of x bar. And so if I do my formula, that's 1 over n times the summation of the expected value of xi. Okay, again, that's because we're playing with this formula. Okay, and so this becomes 1 over n, and so the expected value of xi, we know is going to be a lambda value, but I'm doing a sum of I equals 1 all the way up to n. So this summation, then, if it's the summation of I equal 1 to n of lambda, becomes n times lambda. Okay, and then I'm going to divide that by n, and so this becomes my parameter lambda for us. Okay, and so in this case, it turns out that x bar, if I define it as the sum of xi over 1 over n is actually an unbiased estimator, that my expected value of x bar equals the parameter that I'm after. Okay, because what we did is we said that that was theta. Okay, so the expected value of my theta hat, and that's theta hat, if you will, that's equal to theta. That's the definition of unbiased. So that's the first step achieved on our unbiased. Okay, so now we can go through and we can do our math, and since that's an unbiased estimator, we can very quickly run our calculations. And I'm going to take 18 occurrences at 0 and 37 occurrences at 1, all the way out to 1 occurrence at 7. That number becomes 317. Okay, and so then my estimator for lambda then we said was going to be my x bar, and so that's my estimator. And again, I wrote it as a lambda hat. You could write it as a theta hat. Don't get bogged down on the nomenclature, but really anything with a hat is my estimator. Is going to be equal to 1 over n times the sum of the xi. That's going to be 317 over 150, becomes 2.113. Okay, and so what happens then is that my estimate, which is my sample mean, is equal to 2.113. Okay, this would be the value of our estimator. And that's kind of where we're at on this. All right, so now that we've got that parameter, now we can go in and we can figure out, well, what's the standard error? Get kind of a sense of the measure of the error that we have in this. All right, so the variance of the sample mean then is the variance of xi all over n, that we said that that would be this lambda value, right? And in this case, it's going to be a lambda hat, and that should be my lambda hat value, okay, because that's the variance of my data. Okay, and so then the standard error of my sample mean is equal to then the square root of my lambda hat value divided by n is the definition of the standard error. All right, so then, I know we're writing this a lot of different ways, but you see it written, and I'm pretty bad about being consistent, even myself, that the standard error of x bar is the same as my estimator. The standard error of my estimator would then be the square root of 2.113 over 150 as being my estimated standard error. Okay, now the one thing that you notice in this formula is that as I increase n, this guy gets smaller. If I put 1,000,000 in this thing, this guy goes almost to 0. Okay, and so we can greatly, and again, this is kind of building up to what we've talked about in previous lessons of, confidence in my statistics. And this guy becomes the basics for how I can start establishing what we call a confidence interval. And we'll talk about that, in the next couple of videos. We'll start getting into the actual applications and techniques for using sample data to predict population data. But it all comes out of its roots of coming into point estimation and using that, putting that to work for us. All right, so my sigma, my standard error, just to finish this calculation out, we said was 0.119. Okay, and that's a fairly small value when what did we say the mu was? My mu hat was, what, whatever the value was, 2.113, right? If we use our 96% rule, that's pretty good. That's a pretty small standard deviation on that particular mean value. Okay, and so that's kind of the basics of point estimation. We'll do some more with this, and I'll show you some techniques for how we can construct these estimators in the next video. So if you'll stick around and stay tuned for that, hopefully that'll clarify. Again, this was more about the mechanics and understanding bias and the definition of unbiased estimators and standard errors. But there's a whole lot more to this, even more than what we're going to probably cover in this series. But I just want to give you kind of a taste of where we're going. I've got to have this kind of in my back pocket to be able to jump into actually using statistics to correlate sample data to population data, and eventually be able to use that to do hypothesis testing, where I believe something is true, and then we go and we do a test on it. Okay, so that's kind of where we're headed with all of this. I hope it made sense. As always, if you'll leave leave us a comment down below if you're having any questions on stuff, and as always, like the video if you did like it, and please be sure to subscribe to our channel. We would greatly appreciate it. Hope you all have a wonderful afternoon, and we will talk to you all later. Happy engineering.